Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Welcome to Science in Easy English with Oliver and Lily. Is the universe slowly dying?
For decades, we really thought the answer to that was just a simple, kind of boring yes.
Right.
We thought the universe would eventually end in this slow, incredibly uneventful freeze.
But brand new telescope data suggests we might actually be facing a violent, sudden collapse.
Exactly. Or, honestly, even worse, a literal bubble of pure destruction could be racing toward us at the speed of light right this very second.
Now, see, that is how you start a deep dive.
Yeah.
I mean, we have a massive stack of sources in front of us today to unpack all of this. We're looking at everything from NASA and CERN data to formal surveys of expert physicists and even some really highly insightful Reddit forums.
Yeah, we've got quite the mix today.
We really do. And our mission today is to act as your ultimate shortcut to being well-informed about the ultimate fate of the cosmos.
And, to understand how the universe might die, we first have to really understand what it's actively doing right now, which is expanding.
Expanding. Let's actually ground this right away because expanding space is one of those concepts that sounds simple until you actually try to picture it in your head.
Oh, totally. It breaks your brain a little bit.
It really does. So we know the universe is expanding because of a phenomenon called redshift.
Right.
Imagine you are looking at light from a distant galaxy. As that light travels towards you across the sheer vastness of space, the physical fabric of space itself is stretching.
That's the key right there.
Yeah, so those visible light waves literally get stretched out along the journey, and by the time they reach our telescopes, they've been stretched into longer, redder infrared wavelengths.
Exactly. Meaning, the further away a galaxy is, the more the light is stretched and the redder it appears to us.
So the physical stretching is what we really need to focus on. Galaxies aren't just like flying through space like shrapnel from an explosion.
No, not at all. Space itself is expanding between them.
I was reading through one of our sources, and it offered this brilliant analogy to help you visualize this if you're struggling to picture it. Imagine a tiny ant walking on a giant rubber band.
I love this analogy.
It's great, right? So as the ant walks forward, someone is grabbing both ends of the rubber band and pulling. So the space is actually expanding both in front of and behind the ant.
Right.
The ant is moving, yes, but the ground it's walking on is fundamentally growing at the same time.
That's a perfect way to look at it. And taking that rubber band analogy just one step further, while we can prove the rubber band is stretching, the actual rate at which it's stretching is, it's currently breaking our fundamental models of physics.
Breaking physics, great.
Yeah, cosmologists call this problem the Hubble tension.
Which, I mean, sounds like a phenomenal title for a sci-fi thriller, honestly.
It really does sound like a movie, but it's actually a massive headache for physicists.
Why is it such a headache?
Because we have two main ways to measure the expansion rate of the universe, and they are giving us totally conflicting answers.
Okay, conflicting how?
Well, one way is to look at the cosmic microwave background. That's the relic radiation left over from the very early universe, right after the Big Bang.
Okay, so that's the ancient data.
Exactly. And the other way is to look at modern local supernovae. These are exploding stars that are much closer to us in both space and time.
Let me guess. If our standard understanding of physics is completely accurate, measuring the early universe and measuring the local universe should give us the exact same rate of expansion.
They absolutely should, but the math just doesn't align. The local universe seems to be expanding significantly faster than the early universe data predicts it should be. It's like trying to calculate the top speed of a sports car.
Okay, tracking with you.
One group of mechanics looks at the factory blueprints from the day the engine was built. That's our early universe data. And they calculate the car should top out at 100 miles per hour.
Right.
But then a police officer shoots a radar gun at that exact same car on the highway today, that's our local supernovae data, and clocks it at 110 miles per hour.
Ah, I see. And both the original math and the modern radar gun are technically flawless.
Right.
Which means our fundamental understanding of how the engine works is missing something really critical.
Exactly. And for a while, scientists assumed somebody just made a basic measurement error or, the telescopes were just slightly out of focus or something.
Sure, human error.
Yeah. But recently, NASA's James Webb Space Telescope and the Hubble Space Telescope basically tag teamed to look at this exact problem.
Oh, wow.
They ran the numbers again and confirmed it. This isn't a glitch. The data is correct.
Which really forces the scientific community to admit that we have genuinely misunderstood the cosmos. Like, we are missing a very large piece of the puzzle here.
We really are.
So if the engine is doing something the blueprints say it shouldn't, what is the culprit? I mean, all eyes in the physics world seem to be pointing to one prime suspect, right? Dark energy.
Yes. Dark energy. And to give you some context on why dark energy is taking the blame here, we need to look at the overall composition of the universe.
The breakdown of what everything is made of.
Exactly. Everything you have ever seen, touched, or interacted with, you, me, the Earth, the stars, the galaxies, that everyday normal matter makes up just 5% of the universe.
Just 5%. That is wild.
It is. And then dark matter, which is this invisible substance that exerts a gravitational pull, that makes up roughly 27%.
Wait. If dark matter exerts gravity and pulls things together, but the universe is still expanding,
There has to be a force pushing back.
there has to be some hidden, massively powerful force pushing back. Is that where dark energy comes in?
You've hit the nail on the head. That remaining 68% of the universe is completely unaccounted for by normal physics.
Wow.
That 68% is dark energy. It is the mysterious, completely invisible engine driving the accelerated expansion of the universe. It's actively overpowering the gravitational pull of dark matter.
Okay, so to figure out exactly what this invisible engine is actually doing, scientists built the Dark Energy Spectroscopic Instrument, which is known as DSI.
Yes, DEI.
And it's located at the Kitt Peak National Observatory in Arizona. And I have to say, the engineering behind this thing is staggering.
Oh, it's incredible.
Picture a massive telescope equipped with 5,000 tiny robotic optical fibers.
5,000.
Yeah, and each one of those fibers acts like an independent mechanical eye, programmed to swivel and capture the light from a specific distant galaxy.
And over the course of its survey, DSI is mapping out 40 million galaxies and quasars.
40 million.
Yeah. By doing this, it's creating the largest 3D map of the universe ever made, peering as far back as 11 billion years into the past.
It's mind-blowing.
By looking at how those galaxies are distributed over time, we can see exactly how the rate of expansion has changed throughout cosmic history.
5,000 robotic eyes staring into the deep past. I mean, that alone is wild. But DSI recently released its Year 1 data, which brings us to a massive fundamental plot twist.
A huge plot twist.
Because for decades, the standard assumption in physics was that dark energy was a cosmological constant, meaning its density and its power remain exactly the same over time, right?
That was the assumption, yes.
But the new DSI data shows these tantalizing hints that dark energy is evolving. It isn't a constant. It might actually be weakening over time.
Weakening, yeah. What the data actually shows is a statistical significance between 2.8 and 4.2 sigma.
Okay, translate that for us.
For sure. In the world of particle physics and cosmology, a 5 sigma result is the gold standard for a definitive, unquestionable discovery.
So we aren't quite at the finish line yet.
Not quite. But a 4.2 sigma result is a massive red flag waving at cosmologists, telling them something fundamental is shifting.
But hold on, let me push back on this a little bit, because the history of this whole concept is famously messy.
Oh, it's been a roller coaster.
Right, because Albert Einstein originally proposed the cosmological constant in his equations for general relativity, mostly just to keep the universe mathematically static.
That's to make his math work out.
Right. Then, when Edwin Hubble proved the universe was actually expanding, Einstein called the cosmological constant his biggest blunder and just tossed it out.
Exactly.
Then, in the late 1990s, we realized the expansion wasn't just happening, it was actively accelerating. So, physicists brought the cosmological constant back to explain dark energy.
Yep.
And now this new telescope data is telling us we might have to throw it out again.
I know. It sounds chaotic and maybe even a little indecisive. But
Yeah.
that is the scientific method functioning exactly as it should. We update the models when the data demands it.
Fair enough.
If dark energy is indeed evolving and weakening, it marks the biggest paradigm shift in cosmology in decades. Because if the engine driving the universe apart is stalling out, well, the ultimate fate of the universe completely changes.
So if the engine stalls out, what happens to the car? Because dark energy might be weakening, cosmologists are frantically recalculating the universe's expiration date. And that leads us to a surprisingly imminent deadline.
Though we should probably clarify for anyone listening that imminent in cosmological terms still means billions of years.
Right. Don't panic yet.
But compared to previous estimates of trillions of years, it is a sudden, sharp drop-off.
Let's look at the work of Cornell physicist Henry Tye, who is featured heavily in our sources. He used this new, weakening dark energy data to propose a highly complex model for how the universe ends.
And this model is fascinating. It hinges on two distinct mechanisms driving dark energy.
Okay, what are they?
One is made of ultralight hypothetical particles called axions. The other is a negative cosmological constant.
Let's break down how those mechanisms actually interact. Think of the axion particles like the temporary rocket fuel of the cosmos, right?
Exactly, rocket fuel.
In Tye's model, these axions currently soak the entire universe burning hot.
Bad.
Their massive energy is what is actively driving our current period of accelerated expansion.
Right.
But over time, as the universe stretches and expands, those axions get diluted. The fuel essentially thins out. They lose steam.
And as that rocket fuel burns out, the second mechanism takes over, which is the negative cosmological constant.
The negative constant.
Yeah, if a standard cosmological constant pushes things apart, a negative one acts like a giant cosmic bungee cord. It acts as a brake, actively decelerating the universe's expansion.
Wow, a cosmic bungee cord.
Under Tye's model, because of this intense braking effect, the universe reaches its absolute maximum size in just 11 billion years.
To put that in perspective, the universe is already 13.8 billion years old. So if this model holds true, we are well past the midway point of expansion.
We really are.
To go back to our earlier analogy, it's like the universe is a rubber band that has been stretching for 13.8 billion years. But it's finally about to reach its absolute physical limit, lose its elasticity, and snap violently back.
That snapping back is what cosmologists call the big crunch.
The big crunch.
Once the universe reaches that maximum size 11 billion years from now, it halts, reverses direction, and spends the next 10 billion years collapsing inward.
So 11 billion years of stretching, followed by 10 billion years of crunching. That gives the entire universe a total lifespan of just 33 billion years.
Which is shockingly short in the grand scheme of things. And a big crunch is a profoundly violent event.
I can imagine.
It's essentially the exact mirror image of the Big Bang. As the universe contracts, the physical space between galaxies shrinks. Galaxies are literally forced to merge.
That sounds chaotic.
It is. The ambient temperature of the universe skyrockets as all that energy is compressed. Space gets smaller, hotter, and denser until all matter, all energy, and even space and time itself are crushed back down into a single, infinitely dense point, a singularity.
If you are listening to this and struggling to really wrap your head around reality just compressing into a single dot, you aren't alone. I mean, it is an incredibly dramatic, almost claustrophobic way for reality to end.
Very claustrophobic.
But what if the DSI data is just a statistical fluke? What if dark energy is a constant and the expansion just never, ever stops?
Well, if the expansion never stops, we face an entirely different scenario, known as the Big Freeze or heat death.
Heat death.
Yeah, and this fate isn't governed by gravity or dark energy snapping back. It is entirely governed by the laws of thermodynamics. In a constantly expanding universe, all the matter and energy eventually spreads out so far that the universe reaches thermodynamic equilibrium.
Meaning maximum entropy. Everything becomes perfectly evenly distributed. There are no hot spots. There are no cold spots.
Right.
And because there are no temperature differences anywhere in the cosmos, no work can be done. Energy can't flow. Literally nothing can happen.
Stars will exhaust their nuclear fuel and burn out, plunging the universe into absolute darkness. Galaxies will drift apart until they are moving away from each other faster than the speed of light, meaning they will no longer even be visible to each other.
That's just so bleak.
It gets worse. Researchers at Radboud University recently took this bleak scenario a step further. They applied Stephen Hawking's theories to calculate the ultimate end of the very last objects in the universe.
Hawking originally theorized that black holes aren't entirely black, right? They actually leak radiation over immense timescales, known as Hawking radiation, slowly dissolving like an aspirin dropped into a glass of water.
Exactly. And the researchers at Radboud calculated that this dissolving effect doesn't just apply to black holes. Eventually, even the most durable celestial bodies left over the cold, dead remnants of stars known as white dwarfs will evaporate via Hawking radiation.
Just evaporate into nothing.
They will simply dissolve away into a dilute, invisible gas of photons and particles. The timeline for this total, utter death of the universe is 10 to the power of 78 years. That is a 1 followed by 78 zeros.
I have to admit, I find that deeply, deeply unsettling. A big crunch is a violent apocalyptic event, but at least it is an event.
Something happening.
The big freeze is just a bleak, cold, lonely fade to black. It's an endless, timeless void where nothing will ever happen again.
Is there any loophole here? Like, is it absolutely guaranteed that life, complexity, and order just inevitably succumb to a black void? Thankfully, there are optimists in the physics community who point out a critical flaw in applying heat death to the entire universe. Physicists like Julian Barber and David Deutsch point out that traditional thermodynamics, specifically the rule that entropy and disorder must always increase, is usually applied to a closed box.
A closed box, like a sealed room.
Right. Think of a hot cup of coffee in a sealed room. Eventually, the heat disperses until the room and the coffee are the exact same temperature. No more heat flows. That is a closed system reaching equilibrium.
But the universe is expanding. It doesn't have walls. It doesn't have a lid.
Precisely. Because the universe is expanding without limit, it is not a standard closed box. The maximum possible entropy of the universe is actually growing faster than the actual realized entropy is increasing.
Oh, interesting.
This means the gap between perfect order and total disorder is always widening. Therefore, traditional thermodynamics might not rigidly apply to the cosmos as a whole. Order and complexity could theoretically increase indefinitely.
Meaning life and civilization don't necessarily have to end.
Deutsch even speculates that arbitrarily advanced life might eventually figure out how to harvest dark energy itself. If they can tap into the expansion of space, they could power computation and maintain order forever.
Okay, that is a much more comforting thought. But before we get too optimistic, we really need to talk about the wild card in our sources today.
The wild card.
Yeah, we've looked at freezing, which takes trillions upon trillions of years. We've looked at crunching, which takes tens of billions of years. But there is a sudden game over switch, detailed in the research, that could happen at literally any second.
Ah, yes. You are referring to the Big Slurp.
The Big Slurp.
Which is technically known as false vacuum decay. And this concept moves us away from telescopes and deep into quantum mechanics, specifically regarding something called the Higgs boson. The Higgs field permeates all of space and is responsible for giving fundamental particles their mass. At the exact moment of the Big Bang, the universe was so unimaginably hot that the Higgs field was at 0. But as the universe cooled, the field flipped on, settling into a resting state. We call that resting state a vacuum.
Hold on, let's slow down here. Because you just dropped metastable, false vacuum, and the Higgs field all in one breath.
True.
If you were listening to this right now, your head might be spinning. Let's really ground this. What exactly is a false vacuum?
Fair point. Let's take a step back and use an analogy here. Imagine the universe's energy state is like a heavy boulder rolling down a mountainside. Eventually, the boulder comes to rest in a crater. It looks completely stable. It isn't moving.
Okay, I can picture that.
That is what we thought our universe's vacuum state was, the absolute bottom of the mountain, the lowest possible energy state.
But when scientists finally measured the exact mass of the Higgs boson, The map implied something deeply unsettling.
It implies that the boulder didn't actually reach the bottom of the mountain. It just got stuck in a shallow crater halfway down. It is only metastable.
Vestibule.
It is stable for now, but it has the potential to get nudged over the edge and plummet to the actual bottom of the valley, the true vacuum.
So it's like we are ice skating on a frozen lake, assuming it's perfectly solid all the way down. But we are actually just skating on a razor-thin crust of ice over a bottomless trench.
That is a terrifyingly accurate way to put it.
It's horrifying.
If just one localized pocket of space anywhere in the universe quantum tunnels through that crust, if that boulder gets nudged out of the crater and drops into the lower energy true vacuum, it creates a bubble.
A bubble of true vacuum.
And inside that bubble, the fundamental constants of nature are entirely different. Physics, chemistry, and biology as we know them would instantly cease to function.
And here is the truly apocalyptic part of this scenario. That bubble of true vacuum expands outward at the speed of light. It would rewrite the laws of reality, destroying everything in its path. Stars, planets, human beings, all completely erased.
Is gone.
And because the bubble moves exactly at the speed of light, no warning signal could ever precede it. We would never even see it coming. It would just be, lights out, mid-sentence.
What's fascinating here is how seriously the physics community actually takes this possibility. One of our sources is a recent, highly structured survey of 20 expert physicists. They were asked to estimate the probability of this exact scenario.
And what do they say?
On average, these experts estimated a 45.6% chance that our universe's vacuum is indeed metastable.
That is essentially a coin flip that we are skating on thin ice.
It is, but the survey asked an even more shocking question. If the vacuum is metastable, could vacuum decay be artificially triggered?
Wait, artificially?
Yes. The experts estimated an 18.8% chance that an arbitrarily advanced technological civilization could accidentally or purposefully induce this vacuum decay.
Wait. There is almost a 1 in 5 chance that some hyper-advanced alien civilization could just accidentally push the wrong button in a massive particle accelerator and delete the entire universe.
It sounds like pure science fiction, I know, but it highlights a profound theoretical vulnerability in the fabric of reality. While natural, spontaneous vacuum decay is incredibly unlikely to happen on human timescales, the introduction of advanced technology completely changes the variable.
Because they could manipulate that energy.
Exactly. To induce it, a civilization would have to concentrate an unimaginable amount of energy into a microscopic volume. But if the laws of physics allow it, a sufficiently advanced civilization might eventually build a machine capable of doing it.
Okay, we have covered some incredibly massive, mind-bending cosmic scales today, from the stretching of ancient light to the evaporation of dead stars to bubbles that instantly rewrite reality.
We covered a lot of ground.
We really did. And if you were listening to this, you might be wondering, why should you care about events happening billions or trillions of years from now?
It's a very fair question to ask. As the experts in our sources point out, understanding the absolute beginning and the absolute end of the universe gives profound context to our current existence.
It really puts things in perspective.
When you realize the vast, chaotic forces at play, weakening dark energy, expanding voids, metastable vacuums, it makes the fragile order and the vibrant life we experience right now feel incredibly special. We exist in a rare, temporary window of complexity in a universe that is constantly trying to change its own rules.
It really does make you appreciate the present moment. But I want to leave you with one final provocative thought to mull over, building entirely on that expert survey about the false vacuum.
Oh, I know where you're going with this.
We often wonder why we haven't seen any evidence of advanced alien civilizations. A famous puzzle known as the Fermi paradox. The universe is incredibly old and unfathomably large. So where is everyone? Well, if highly advanced technology is capable of accidentally triggering a big slurped vacuum decay, could it be that an ancient civilization somewhere out there in the cosmos already pushed the wrong button? Could a bubble of absolute destruction be quietly racing toward us at the speed of light right now, having already wiped out the rest of the galaxy?
That is certainly a dark but mathematically plausible way to solve the Fermi paradox, and it is a perfect reminder that the science of cosmology is still actively evolving. The deeper we look into the dark, the more profound questions we uncover.
Thank you so much for joining us on this deep dive. Keep looking up, keep asking questions, and maybe, just maybe, enjoy that ice skating while the crust is still holding. We'll catch you next time.